So I'd like to present to you a discovery and a product. So this is in the category of big data, weather history time machine, and global warming visualization. So this is the first discovery. So what we discovered is that we used advanced mathematics and statistics. We discovered that in January 1998, the big El Nino, and there was cold water in the depths of 100 meters down in the ocean, in the eastern tropical Pacific. Now we know this is the cold water here. So stretching from here to here is 7,000 kilometers. Now we know that the El Nino has a warming over the eastern part of tropical Pacific. That's why we get a lot of rain this year. But people do not know that. Actually, down in the ocean, there was cooling part. And it's very big cooling. It's 5 degrees Celsius below normal. Okay, that's a huge one. So this could only be done now with this mathematical method, because at that time there was no buoy, no Argo buoy observation down there. You could not observe. Okay, you could only observe called sea surface temperature. So this discovery was made jointly with NASA JPL, with grad student and a scientist. A mathematics novelty in this discovery is basically the singular value decomposition called SVD applied to the big space-time data. This is a famous Jane Goulab 1965 paper, and he was elected to the National Academy of Science because of this, and he was also elected to the National Academy of Engineering, one of the very few mathematicians who has made to both academies. Jane Goulab actually visited us a few years ago, and so SDSU is actually a stronghold of linear algebra related to SVD. And our former department chair, David Carlson, who was the associate editor for linear algebra and its application for over 10 years. And Steve Pierce moved here from University of Toronto as a tenured professor. And also Bob Gruen moved here from Auburn University, also as a tenured professor. So I'm doing a bit of research in this direction now. Now, so if you look at this space-time data, so every data you observe, you have a space and time. Where did you observe it? When do you observe that? And then you can decompose that into the spatial part and the time part. And then it's linked by energy. That we are doing SVD every day, every time. So what do? We see our eyes. That's the space part. We see who you are. And then our brain memorize what's going on. So that is time part. So you have this time part. And then linked by energy, that's what we hear. That's how big is the energy. I speak very loud, so you can hear me, right? So that's the energy. So that's here. And then it's quantum mechanics, same thing. So you have a Schrodinger equation. This is MIT instruction slide. So you have a Schrodinger equation, and then you have a space and the time decomposition, and you have energy here, and then that becomes called a mathematically eigenvalue problem. Okay, so this is a universal law, and we have used it wisely in the climate area. And next I want to talk to you about a product. So this is called a climate time machine. And when this product was released 2 years ago, this was covered by media around the world. Our SDSU media team did a great work. So this was covered by New York Times, by many places. And I got emails from India and Italy. They want to market my products. But eventually we filed a patent. So I thank my really brilliant students for helping me to turn my dream and mathematics into products. And one of them is here, Gregory Clark. Greg, right here. And he is going to work for Spare War. So let me show you one little report from local. That's the KUSI TV. And so let me play this TV interview. No, the TV. What happened with TV? This is the VGI. That's the big problem. The VGI is not fast enough. This is big data. You need HDMI. So the VGA is not very good. But you hear this. Maybe. Maybe. Oh, okay.
Okay, thank you very much. These two guys
do you have a way to do it?
Smart. They're brilliant. And so I'm getting a little bit intimidated because you're very smart. You guys have developed a software.
Do you have HDMI? Yeah.
To look at historical weather data. Most importantly.
Okay, so we'll switch to big data, kind of fast transmission. It's because my talks often go like, my one talk goes like, often go like 500 megabytes a talk. Hopefully it's okay. What happened? Oh, there's no sound. Was that or was no sound? Where did the sound come up? The sound is not okay. High tech has problem. The sound. Yeah. Okay, let's go that. Okay. So what this is that let me use this report to tell you this product. So what the product is, you can go back to its history. You want to say that, well, I want to know that January of 1918, what is the rain? Was the rain, a lot of rain or no rain? So, and then you can go back to that. So we have this, we have a data, we have a picture, and then we have a time series. So that you just click on that, you get all this stuff. And now I can show you a new system, which even have a higher resolution for the whole globe. So this is a very funny title that I put it here. So it's called New Climate Time Machine is not a DeLorean, like you have seen the movies, right? And then, but it's almost as cool. I really like this title, so I show this. I think that the reporters are very creative. So they turn my kind of science product into a good stories, and they market it really well. So we are now in the new stage. We're building a new time machine. The new time machine is a four-dimensional big climate data visualizer. So this is this big data technology. And the mind behind it is Tom Carr. So he is a collaborator. We published a couple of papers together, and is now the director of NOAA National Center for Environmental Information. So that's he's NOAA data king. So he controls the data from all the way to solid Earth, to water, to sky, and to up sky. So he was a former president of American Meteorological Society. It's not a math society, so AMS. And he was aide to Vice President Al Gore during the Clinton time for the global warming studies. So what is the new technology about? It's about the idea to build a Hadoop distributed file service system. So for multi-petabytes of climate data. So the current system and the past system is that, so you have one server, and then you have clients to download the data from the server. So in the last 10 years, it's very normal for a grad student or postdoc to spend 1 month or first 2 months to download 500 gigabytes or 1 terabytes of data to do the research. So now what are we going to do? So we're going to build mirror images. So we built like up to 6,000 mirrors that is allowed in the Hadoop system. And then you can download the data, same amount of data, literally within 1 hour. So a pilot NOAA funding was already allocated, and then these two gentlemen just signed, agreed with it, said that we should take the money. And I think there is a risk they don't want to take the money. So we will install the system in museums and universities and schools. The system will facilitate climate education by introducing climate data sets into college and school classrooms, student homework, and course projects. So SDSU Big Data Master's Program will be helpful, and it will begin in the fall of 2017, so next year. So this is led by Geography Professor Min Su, and the president, our president, Hirschman, has supported this, and he has awarded a PAF award for this project. So hope that everybody else will support it too. Okay? If you don't support it, let me know. Let me know early. Okay? So we can explain that to you. I don't want you to stop it. Okay? So I know that some people want to stop it. So next, I will brag about SDSU's prominence in the world. So that's what Stanley told me, is that it's brag about it. That's what we want people to know who we are. Right? So one is that we are working hard to support the SDSU's strategic plan of building on excellence and campus-wide mobilization for cross-disciplinary collaboration. I think that Steve Welter started this centers. I think this is great. Now we are producing things now. We are modernized the SDSU NASA carbon flax database. This is started by Walter O'Shea, the distinguished professor in biology. Now this is the longest history in the world. And now we rebuild that so that more people can use it. So I can get, yeah. So other one is that this figure is the first estimation of the uncertainty of global warming. And then this was computed by my theory. I was the co-author of this. Now this figure was published in 2001. And then after the publication, literally, this figure was shown around the world hundreds of times a day. And many people have seen this several times. So Steve told me that he saw this when I showed that during my Johnson lecture time. So I saw this figure before. so basically, this figure was shown or read by president of every major country. So now what's new? The new is that last year there was a science paper published by Tom Carr, the same person. Okay? So he pointed out that the possible artifacts of data bias in the recent global warming hiatus. So there's no such a thing. So I just plotted this. His aides contacted me 3 months ago. I plotted this, that we don't see this the hiatus things. Okay? And then not only we do research and teaching, but also we serve the community. So what we want to do, we want to turn this finest city in America into a better city. So in summary, we have made a discovery. Okay, that's the cooling part in the deep ocean. And we have generated a product, that's a weather history time machine. Now we're going to build a bigger system, a big data system, and we'll modernize the NASA carbon flax database. Now we have a plea, finally. The SDSU communities support excellence and prominence. Faculty keep promises and deliver. Faculty and administration work together to hire the best people in order to build a strong and world-prominent SDSU. Thank you very much for your attention.
Questions?
Sam, in your time machine calculation for dynamic and spatial temporal resolution, deviations or uncertainty levels, do they have any correlation between how far you go back or for at least the part that you can confirm?
Of course, yes. When you go back, then you have fewer data. Let me show you here. That's actually we have this prototype of machine is already for the big data machine is already built. So we can show all kinds of things. Like just give you one example. Just for so you can say look at parameters. Say, well, let's look at temperature. So let's look at say time. So you say I want to say August of say January of 1934, for instance. And then you can just slide this or just type this whatever to that, and then you can use the 3D or 4D. You can zoom in or zoom out. You know you can do 2D, for instance. And if you say well you want to zoom in and zoom out, you do all kinds of things. And then say well I want the data. I want the digital. So what you do, you go to the data download, and then you say that download the data, grid the data. So then the data will be in your CSV file, and then it's all here. And then you can do research and plot. Okay? And then say, I want to know the history of San Diego. So what are you going to do? You click San Diego area, for instance. So you can close this, and you get to San Diego area, and then you say that I click that point. And then you say, well, is that the point? It's almost 31 degrees, so it's supposed to be 32. And you click on that, and then you will see the history. And then, so the history will come out. And then we'll tell you, you can know exactly which year and in which month, you know exact temperature. Okay? So this is something we need in our teaching, in our classrooms. Otherwise, we talk about warming, you say, well, what's the number?
Can we see the four-dimensional data?
4D, this is 4D, the time space is 4D. So that means 4D means that we go deep in the ocean and up in the sky.
It's just hard to show on the screen. Other questions?
This is talk about, what I did here, you're talking about like 300 gigabytes, and then it's times 30 times when we do calculation.
Sam, the power of big data to inform us about the past is really fascinating. It is fascinating. But I like to look at the prospective aspect of the time dimension. To what extent can you use your model to predict any of the variables that you can tell us about for some time in the past? What's the predictive value of your data set?
We're not predicting. We go back to history. We're not predicting the future.
But could you?
We go back to, this is 1851.
Could you?
We could not. If you want to predict the future very accurately, you're better than God. That's not right. Okay?
Sam, but speaking of predicting the future, so a question asked earlier really is what are the error bars as you go back?
Yes.
So you're not showing error bars here, but further back in time, are those bigger error bars than closer to the present, where presumably we have better measurements?
Well,
I think
definitely.
that relates in part to the question.
Okay, here, let me show you that.
I think you're off, aren't you? No, not quite.
So this is the error bar. You can see that? This is the first error bar we estimated, and that was used by IPCC was done in first we started work in 1998. I was published in 2001. Yes, indeed. Well, I'd like to predict, but we're working on that. With our next proposal will be on prediction, but not as good as this. Yeah. And that means people want to predict even 1,000 years ago. Farmers always, I want to know what's the weather tomorrow. Yeah.
And to Radmila's question and your response, my sense is you are manipulating data here. You don't have underlying physics about the atmosphere which allows the models to predict. You're taking data and you're using it in a very sophisticated, complicated way to predict, to see what happened in the past. But to go into the future and not just extrapolating from the past, you need to have an underlying model, and that's not what you're doing at this point. Is that correct?
We use model. We use model. That's why we do statistics differently from the past in the climate community. We use models, so we produce dynamically coherent structure. That's what was wrong in the past climate research was they used statistics only. They did not use model. And our structure, the SVD, collect model and look like it's the quantum mechanics. They're a physics professor, right? So quantum mechanics. So that means that we use model to do the SVD. Okay. Yeah. So we try to use the most advanced mathematics available so far.
Thank you, Sam.
Okay.